Hello, my name is Raad Raqaji and my two partners are Qasem and Abdirahman, and in this video clip we will be talking about the electric flux and Gauss's law. This video will be presented into three parts. First, I will be explaining the electric flux, how it works and what does it do in more details. Then Abdirahman will be explaining what Gauss's law is, and then finally Qasem will apply the Gauss's law to find the solution of the uniformly charged non-conducting sphere and more and deep details. Electric flux is a measure of electric field perpendicular to a surface, or the number of electric field lines passing through a given area. Therefore, if the area of the surface was greater, the flux will increase. In a similar way, when the area of the surface at an angle where there are no electric field lines go through it, there will be no flux. Electric flux is defined as the product of electric field B and the surface area A. Electric flux has a CI unit of voltmeter and a Newton meters squared per coulomb. The magnitude of the electric field at a distance from a single point charge is given by E equals K times Q divided by R squared, where E is the strength of the electric field around point in Newton coulomb per coulomb, Q is the charge that creates the field in C in coulombs, R is the distance from the charge in meters, and K is constant as 9 to the times 10 to the power of 9. The magnitude of E that is determined is independent of the values of the test charge and depends only on the charge Q producing the field. This formula can also be referred to as Coulomb's law, in this case for determining the magnitude of the electric field producing by a point charge.
Hello, my name is Abdirahman Hagi. As Raad stated, the electric flux is a measure of the electric field lines through any given surface. With our understanding of electric fields, we can determine the number of lines within an enclosed space by using Gauss's law, which is an important physics law. The law states that the net flux of an electric field through a closed surface is proportional to the enclosed electric charge. Calculating the electric flux of a point charge Q through a small portion of the overall enclosed surface is given by this formula, where E is the electric field and A is the area. However, the formula provided solves only for the number of electric field lines going through a specific portion of the area. So to find the total electric flux moving through a surface, we need to simplify and integrate the equation. From the original equation, E is substituted with its counterpart. The equation is then integrated. Since E is a constant, it doesn't need to be integrated, leaving dA to be integrated. The integration of dA equals 4 pi r squared. After removing all the like terms and simplifying the equation, we are left with a simple equation that solves for the total electric flux through a surface, the sphere surface. When determining the electric flux through an enclosed surface, it is possible for the Gaussian surface to have a net flux of 0. There are multiple reasonings for this. One reasoning occurs when a point charge lies outside the surface. This is because every line that enters the surface must leave the given surface, meaning the net movement through the given surface is 0. Another reasoning for the net flow of 0 occurs when the charges of equal and opposite signs are included within an enclosed surface. This happens again because each field line that enters the enclosed surface must leave. For cases where there are multiple point charges within the Gaussian surface, the electric field lines present at a specific point are summed together. When using the Gaussian law formula, note that Q enclosed is the sum of all point charges within a given surface. When observing space 4, which is denoted as S4, we see that it contains all point charges that are visible. So the equation will be written as flux equaling Q plus Q plus Q plus Q minusing 2Q divided by epsilon. The Gaussian surface isn't used to correspond with real physical objects. It is an imaginary ideology that is used as a mathematical construct that enables users to have a greater understanding of electric flux. Depending on the charge distribution, the Gaussian surface shape will be determined. For 1/2 dimensions or a charged rod, a cylinder Gaussian surface will be required. However, if the charge distribution has 3-dimensional distribution or a solid sphere of charge distribution, then a Gaussian sphere would be chosen.
Hi, I'm Qasem, and in this section we will start by talking about the application of Gauss's law. We will try to solve the electric field of a uniformly charged non-conducting sphere for a point inside and outside the object. To understand our object, we will draw a sphere with a radius of r0, and that non-conducting sphere is uniformly charged towards its volume. We will assume that it's positively charged, that is represented as the positive signs, and the 2 points are first a point outside the sphere with a distance of r where r is greater than r0, and the second point is inside the sphere with a distance of r where r is less than r0. Since we have a clear vision of the problem, now we will try to solve the electric field on the 2 points by applying Gauss's law, which states that the electric flux represented by the dot product of the electric field strength and the surface area is equal to the charge enclosed over the constant epsilon naught. And because both the area and the enclosed charge need a Gaussian surface, we will start by creating not one but 2 Gaussian surfaces, one inside and one outside the sphere, where the 2 points lie. Both surfaces are spheres because we are dealing with a 3-dimensional charged object. Now we will only focus at the point inside the sphere where r is less than r0. Now, since the electric flux is the dot product of the electric field and the Gaussian surface area, we can remove the dot product by adding cosine theta to the equation. And since the Gaussian surface is a sphere, that means that the direction of the electric field is parallel to the direction of the normal of the area at any point of the sphere, thus making theta equal to 0. And cosine of 0 is equal to 1. We can remove it from the equation. In addition, we can say that the electric field on the Gaussian surface is constant in magnitude and direction due to the symmetry of the charge distribution. Therefore, it can be taken outside the integral. Before proceeding to solve the problem, we will explain what is the charge enclosed by the Gaussian surface. Since the charged object is non-conducting and the charge is distributed throughout its volume, we can say that the charge density is the ratio of the charge per volume. Thus, the charge enclosed by the Gaussian surface would equal the volume times the density, and the volume of the Gaussian surface is simply the volume of a sphere. Then, the equation would be as shown. Now we can simply add the integral of part of the cosine surface to be equal to just the area of the sphere. We can simplify the equation by crossing out the like terms to get the final equation. The electric field strength for a point inside a non-conducting sphere is equal to the density of the object times the radius or the distance from the center point divided by 3 times epsilon naught. Now we will find the electric field for a point outside the sphere using the same steps. First, we will simplify the dot product since the direction of the electric field is parallel to the direction of the area. Then we can take the electric field outside the integral due to symmetry, using the same ratio of charge, but now the volume is for the total of the sphere, that has the radius of our node. In the end, the electric field outside the object is equal to the density times the radius cubed over 3 times epsilon naught times the radius squared. And if we represent both equations on a graph, it would show that the electric strength inside the object will increase at a constant rate till the surface, then decreases. I'd like to thank my team for putting together this video, and thank you for watching. See you next time.